Okay, so we want to prove that if A, B, and C are any three events, then the probability of A and B and C occurring, right, would be equal to the probability of A occurring times the probability of B occurring, given that A had already occurred, times the probability of C occurring, given that A and B had already occurred. So, of course, in order to do this problem, in order to prove this theorem, we need the definition of given or the conditional probability, right? So, this is the definition. Probability of W given Z is equal to the probability of W and Z occurring over the probability of Z occurring. So from this, I'm going to multiply both sides by the probability of Z to get the probability of W given Z is equal to, the probability of W given Z times the probability of Z is equal to the probability of W intersection Z. So we're going to be using this in order to prove our theorem. And what I'm going to do is I'm going to mark up, I'm going to have this be blue, the W's be blue, and the Z's be purple. You'll see why in a second. Okay, so let's go ahead and start our proof. So we have the probability of A intersection B intersection C. So notice in my theorem, I want A intersection B together and C all by itself, right? So what I can do is I can rewrite this as the probability of A intersection B together, grouped together, and then intersection C, right? Because I know sets under intersection are associative, right? All right, so now what I'm going to be doing is I want this Z here. I want A intersection B to be the Z. So let me go my markup. So that means for A intersection B, that's going to be my purple, right? And then my C is going to be blue. Okay. So notice here, that means I need to flip them a little bit, right? So let me go ahead and flip them. So that means the probability of C intersection A intersection B, right? So it's exactly like my um, definition above, right? Right here. So let me go ahead and continue with the markups. So C is my blue, and A intersection B is my purple. Okay. All right, so now this is equal to, so now it's going to be the probability of C given A intersection B, right? Blue given purple, times the probability of purple, right? So let me go ahead and mark those up again. So the probability, let's have A intersection B as my purple, right? And then C is my blue, right? So now, notice, at least for my theorem, I have C given A intersection B, right? I have C given A intersection B. Now, probability of A intersection B is going to be the probability of A times the probability of B given A, right? So let me go ahead and this is equal to the probability of A intersection B times the probability of C given A intersection B. All right. So this is equal to, so the probability of A intersection B, right? So I want A by itself and B given A, right? So let's see. A by itself, so A must be purple, right? So let me do purple here. Markup. So purple must be my A. And blue must be my B in this case, right? Notice here, W given Z, I want A by itself. So that means A's got to be the purple because that's when A would be by itself, right? Okay. So let me go ahead and go down a little bit. There we go. Perfect. So this is equal to, so I need the B over here, right? So let me go back a little bit. So this means I need probability of B intersection A times the probability of C given A intersection B. And now, so of course with the markups, so blue is here and purple is here. Okay, so now this is equal to, so it's going to be blue given purple, so the probability of a blue given purple times the probability of purple times, so that's this right here, right? That's the purple for the A, and then blue for the B, right? So drawing, and then times the probability of C given A intersection B. Okay. All right, this is equal to the probability of A times the probability of B given A times the probability of C given A intersection B. All right, and that's exactly what we wanted to prove. Thus, the probability of A intersection B intersection C is equal to the probability of A occurring times the probability of B occurring given A already occurring times the probability of C occurring given that A and B had already occurred. And that is our proof.